Hi, welcome to Hubble's Universe Unfiltered. I'm Dr. Frank Summers of the Space Telescope Science Institute. You may remember that in May 2009, astronauts aboard the Space Shuttle visited the Hubble Space Telescope for a servicing mission. It was an incredible servicing mission. They put in 2 brand new instruments. They repaired 2 old instruments, which, by the way, weren't meant to be repaired in space. They replaced the batteries, put in new gyroscopes, added in some thermal insulation. It was the most ambitious servicing mission ever attempted. And it was incredible that they completed everything on their to-do list during their 5 spacewalks. Wonderful, wonderful accomplishment. But here it is September 2009, and we've been getting questions. Well, did it work? Was the servicing mission successful? Where are those beautiful images from Hubble? Well, during the summer of 2009, we've been doing what we call Servicing Mission Observatory Verification. It's a very long, slow process whereby we bring up the new instruments to speed, we check them out, we calibrate them, we go into the old instruments and verify that they're working, we recover their science capabilities, and it really does take several months to do this. But now, we're finally ready to show you the brand new images from Hubble. Well, actually, you got a sneak preview last month. Now, you may remember back in 1993 and 1994, when 1993, this object was discovered. This is comet Shoemaker-Levy 9, and it's a comet that was discovered in orbit around Jupiter and had broken up into about 20 or 30 pieces. When the orbits were calculated for this comet, they found that it was going to smash into Jupiter. Sort of like, well, this is a montage image. We've got the image of comet Shoemaker-Levy 9 and the image of Jupiter, making it look like it's going to come smashing in. Well, that's exactly what it did. And in July 1994, Shoemaker-Levy 9 smashed into Jupiter. These small pieces of comets basically exploded as they came through the atmosphere, and they created these big, dark holes in Jupiter's atmosphere. We sort of call them bruises on Jupiter. Now, impacts like this have occurred throughout the history of the solar system, but this was the first time we had ever seen these impacts happen. And so this was an incredible event covered by all telescopes, including Hubble, and we told you it was a once-in-a-lifetime event. Fortunately, we were lying, because it turns out to be a twice-in-a-lifetime event. In July 2009, an amateur astronomer in Australia took another image of Jupiter and saw a dark spot in its southern hemisphere. Telescopes from around the world quickly turned to Jupiter and confirmed that, yes, this looked like another impact event. This was an important enough event that we actually stopped the SMOV operations, and we used our new camera, Wide Field Camera 3, to take this image of Jupiter. And in the southern hemisphere is that dark spot. Let me bring that up a little bit more detail. It was important to have Hubble take a look at Jupiter because Hubble has the highest resolution of visible light of any telescope. So we're going to see details with Hubble that we couldn't see with other telescopes. And here you see the dark spot, and it's sort of elongated. This is about a week after its discovery. It was more circular when it was discovered, and the rotation in Jupiter's atmosphere is actually stretching out the dark spot. Like Shoemaker-Levy 9, the bruises in Jupiter's atmosphere were not permanent. This one, by the middle of August, was stretched out into a long, thin line and will eventually disappear. Now, these images were taken with Hubble's brand new camera, Wide Field Camera 3. It's the replacement for this instrument, Wide Field Planetary Camera 2. This is actually astronaut Drew Feustel on the robotic servicing arm after having put in Wide Field Camera 3, and he's now stowing Wide Field Planetary Camera 2. We have 4 new images from Wide Field Camera 3 that we're going to showcase, and they're going to show some of the amazing things that Hubble can now see. One of the first images that we're going to take is of a planetary nebula. This is a planetary nebula called the Helix Nebula. Now, planetary nebulae have nothing to do with planets. They're actually the death of a star. This star in the center isn't really a star. It's what we call a stellar remnant, or a dead star. It's a white dwarf that has gone through all its nuclear fusion at its core, and as it's in its death throes, has blown off its outer layers to create this beautiful nebula around it. So a planetary nebula is really the death of a star, somewhat like the Sun, maybe a little bit more massive than the Sun, that creates a beautiful planetary nebula that exists for about 30,000 to 100,000 years. And these planetary nebulae are absolutely gorgeous. This is sort of a typical one that looks like a ring. We also have some that look like bubbles. This one is called the Spirograph Nebula. It's got a big bubble shape to it. We have some that look like cylinders. You can see this is a cylindrical one with holes at either end down here. We have some that look like hourglasses. It's sort of pinched in the center and has an hourglass shape out here and an hourglass shape out here. We have some that look like fireworks explosions. And then we have one called the cat's eye that, well, you tell me what it looks like. This is amazingly complex, all sorts of stuff going around and big shells coming out. This is planetary nebula are some of our most gorgeous Hubble images. And there are about 20 or 30 more. So you wouldn't think we could come up with something even more beautiful, but we did. This is the Wide Field Camera 3 image of the Butterfly Nebula. And it really does look like a butterfly as defined by its sort of hourglass shape, sort of pinched in the center and flowing off up and down in the hourglass directions, being the wings of the butterfly. There is so much really gorgeous structure in here. Let me take you in this region here. We'll blow that up to full screen, and you can see the sort of the cosmic landscape going on here. The energy is flowing out from the white dwarf star in the center and flowing across here, creating this is just a gorgeous landscape. And the same thing is happening in the other direction. The energy down here, when we pull that up to full screen, you can see that the high energy radiation and the winds of the gas flowing out create a really beautiful landscape of material in this planetary nebula. Now, this shows you that Wide Field Camera 3 is working. But what it doesn't show you is the unique capabilities that make Wide Field Camera 3 such a special instrument on Hubble. In order to explore that, we're going to take a look at a globular cluster. This is an old image of a globular cluster from Wide Field Planetary Camera 2. It's the globular cluster Messier 80. And globular clusters are collections of tens of thousands to millions of stars that all orbit around one another. And this one is a relatively small globular cluster. It has about 50,000 stars. The other special thing about globular clusters is that they are all old stars. These stars are about 10 billion years old. So you won't see any bright blue or white stars. You'll see mostly yellow and orange and red stars in globular clusters because those are the stars that live longer than about 10 billion years. The blue stars, well, they die in hundreds of millions of years and they wouldn't be in globular clusters. Now this is a wide field image of a globular cluster. If we look into a detail into a globular cluster, this is a detailed image, again with Wide Field Planetary Camera 2, of the globular cluster Omega Centauri, one of the largest globular clusters in our galaxy. And again, you see lots and lots of yellowish stars, but you do find a few blue stars. And that's actually what the science behind this observation was about, trying to find those few blue stars. And you can see it's sort of like trying to find a needle in a haystack. Well, we took another image of Omega Centauri and we used the ultraviolet and infrared channels with Wide Field Camera 3, and we were able to get this. Notice that we were using just the ultraviolet and infrared capabilities of Wide Field Camera 3, and all of the main stars, all of those yellowish stars, are now diminished. Instead, all of the blue and red stars now start to pop out. Let me show you some detail. We're going to take a look at this region down here at full screen. And here you can see that these blue and red stars just pop out. Why? Because the hottest stars are the only stars that will be emitting heavily in the ultraviolet, and the coolest stars are the only stars that will be emitting heavily in the infrared. Wide Field Camera 3 has greatly increased sensitivity in the ultraviolet and enhanced coverage across the wavelength regions. And so by using Wide Field Camera 3 to observe globular clusters like this, we can truly find these needles in the haystack much more easily. Now, for this globular cluster, the important thing is looking in the ultraviolet, where we have greatly enhanced sensitivity. But Wide Field Camera 3 also has a separate infrared channel that helps us when we're looking at nebula. And we're going to look at this pillar in the Carina Nebula. Now, these pillars are really just gorgeous structures. This one is about 3 light years long. And if I zoom in on it, you can see what's happening here. All of this brown stuff, this is the dense gas of the pillar. And way out here, there are some really hot, bright stars that are shining down on this pillar. The high energy radiation from those bright stars is heating up the dense, cold gas and making it stream off. It's sort of evaporating away. and it makes for a really gorgeous image. And now we've seen lots of pillars like this, both in the Carina Nebula and in the Eagle Nebula and several places. But what makes this observation really cool is that if you looked at this same pillar in infrared, it would look like this. It sort of disappeared. It became sort of a ghost. And that's really what's happening because the infrared radiation is longer wavelengths and it makes it through that dense dust and you can see into the pillar. Matter of fact, if we go in a little closer, we take this close-up image, take a look at this star here. When we then look at it in the infrared, pop, you can really see that star. Matter of fact, if you go back and forth between the visible and the infrared, you can see lots more stars in the infrared because you're looking deep into the pillar and you're seeing the stars that are embedded in it. Matter of fact, this star is very special because you can see there are jets extending off in this direction and in this direction. This is a newly formed star. As stars form, they tend to emit jets of material streaming off in two directions. And here you can very clearly see the jets in the infrared version of the image. Now, to sort of summarize the idea, this is a composite image of both the visible light and the infrared light. Taking half visible and half infrared, you can see the structure of the pillar, but you can also see these jets, and you can really trace them extending across the image, going out to this way and all the way out to some clouds out here. So this newborn star creates jets that extend for about 10 light years, the pillar itself being only a few light years in length. This illustrates the enhanced ability for astronomers to see in the infrared with Wide Field Camera 3. Now, our fourth image is an image of a galaxy group called Stephan's Quintet. As the name implies, it's 5 galaxies. Really, you can see 1, 2, 3, 4 objects here, but this object is actually a double object. If I zoom in on it, you can see there are 2 centers. These are actually 2 galaxies that are smashing together. They are interacting. And the evidence of the interaction is in that their structures are distorted, and you get these pink and blue regions along here, which are as evidence of new star formation. When galaxies interact, the gas clouds tend to collapse, and you get bursts of new star formation. You can also see in the larger image that, well, one of these things doesn't really look like the others. You've got mostly yellowish, yellowish, and yellowish, but this one here is rather bright blue and pink. This galaxy is not actually part of the group of galaxies. This is a foreground galaxy that is only about 40 million light years away, whereas the rest of the galaxies in Stephan's Quintet are around 290 million light years. So this is actually at 1/7 the distance. And in order to appear about the same size, it's actually a small galaxy. This is a small, what we might call a dwarf galaxy, but you can see it's undergoing immense amounts of star formation because you've got lots of pink and blue regions that indicate that star formation is going on. So what we have here is a group of 4 galaxies plus a galaxy in the foreground that happens to be projected upon them, and that's what makes up our galaxy group, Stephan's Quintet. So these are the 4 images from Wide Field Camera 3. Omega Centauri, a pillar in the Carina Nebula, the Butterfly Nebula, and Stephan's Quintet. Including the Jupiter image that was released last month, we have planets, stars, nebulae, and galaxies. The universe is back. But these are images just from one instrument on Hubble, Wide Field Camera 3. The other instruments are also working. This image here is of the galaxy cluster Abell 370, and it was taken with the Advanced Camera First surveys, and it shows that ACS is working. Now, this image is really cool. Don't have any time to explain it to you. All sorts of gravitational lensing effects. Take a look on the website and you'll find all the details. Also, we have the new instrument, the Cosmic Origins Spectrograph, also known as COS. And this observation was released. It's an observation of this sort of dot here. It's called a quasar. And this quasar is really, really distant across the universe. And there are clouds of material in between us and this quasar, but we can't see them with an imager. What we need is a spectrograph. We need to spread the light out into its spectrum, and these absorption lines in the spectrum show us the clouds between us and this quasar. That's what COS does better than any instrument anywhere, and cost is up to speed. We also have the Space Telescope Imaging Spectrograph, otherwise known as STIS, which does spectroscopy but of a slightly different kind. Instead of just taking a spectrum of a single point, it can actually take a spectrum of a whole slit of points. And this is an example using the object Eta Carinae, and STIS took the spectrum all along this slit and stretched out here. So each layer along here is a different spectrum of a different point on Eta Carinae, and you can see that the spectrum are different, and you can identify not only the composition but also the motions within Eta Carinae using Space Telescope Imaging Spectrograph. Plus, there is a bonus. The Near-Infrared Camera Multi-Object Spectrograph, also known as SNCMOS, stopped working last September. We were unable to get it restarted last September after a software upload. Well, in August of 2009, we figured out the correct starting procedure, and NCMOS has now cooled down to its very low operating temperature. So NCMOS is back. Hubble now has a full suite of scientific instruments. Hubble is back in business, and it is better than ever. This is the best Hubble ever. It is now back in science observation mode. It is taking incredible observations, creating fantastic images, and making amazing discoveries that I'll be able to tell you about in future episodes of Hubble's Universe Unfiltered. Now, if you have any questions about this episode, or maybe you'd like to suggest topics that we could cover in future episodes of Hubble's Universe Unfiltered, well, you can reach us on Twitter. We're available at twitter.com/Hubble's Universe. Send us a message using the @Hubble's Universe tag, and we'll try to respond to it. That's all for today. We'll see you next time.